Welcome to BioinfoBytes. Today, we're going to decode a true cornerstone of bioinformatics, the Needleman-Wunsch algorithm. So imagine you've got two sequences. Could be two genes from different species. You want to know just how similar they are, but not just in one spot. You want to compare them across their entire length, from the very first letter to the very last. How do you find the single best way to line them up? Well, this is the exact problem that Saul Needleman and Christian Wunsch cracked way back in 1970. Their algorithm gives us a guaranteed, definitive method to find the optimal global alignment. It ensures you find the best possible score for a full end-to-end comparison. Okay, so what exactly do we mean by global alignment? It's pretty much what it sounds like. It's an alignment that stretches over the entire length of both sequences. The whole idea is to maximize the number of matching characters from start to finish, even if it means we have to strategically introduce some gaps along the way. But, global alignment has a famous counterpart, local alignment. While global alignment compares sequences from end to end, local alignment, which you'd use the Smith-Waterman algorithm for, just hunts for the single best matching region. Here's a way to think about it. Needleman-Wunsch is like comparing two full portraits to see how similar they are overall. Smith-Waterman just checks to see if they happen to share the exact same smile. So how does this thing actually work its magic? Well, the algorithm uses a really elegant and powerful process called dynamic programming. Let's break down the mechanism. First off, the algorithm needs some rules to play by, so we set up a scoring system. This basically defines the value of every possible move. You get a positive score for a perfect match, a small penalty for a mismatch, and then a bigger penalty for a gap, which represents an insertion or deletion. These scores are absolutely crucial because they guide the whole process. Believe it or not, this whole complex problem gets solved in just two key steps. First, we build and fill a big grid, which we call a score matrix. Second, we trace a path backward through that matrix to reconstruct the actual alignment. That's really the core idea. Fill the matrix, then trace it back. All right, let's focus on that first step, filling the matrix. You put one sequence along the top of a grid, and the other one goes down the side. Now, every single cell in this grid is going to hold a number. That number represents the best possible alignment score for the parts of the sequences leading up to that exact point. And to calculate that score, we only need to look at 3 of its neighbors. So to get the score for any new cell, the algorithm looks at 3 possible moves. Coming from the diagonal means we're aligning 2 residues. Coming from the cell above or from the left means we're introducing a gap. The algorithm calculates the potential score from all 3 moves and always chooses the one that gives the highest score. It just repeats this process cell by cell until the entire matrix is filled out. Okay, once the matrix is totally full, we get to the really cool part, the traceback. This is how we build our final alignment. We start at the bottom right corner and trace the path of highest scores all the way back to the top left. A diagonal step tells us we have a match or a mismatch. A vertical or horizontal step, that means a gap. This path literally reveals the optimal global alignment. Now, this isn't just some abstract computational exercise. Its impact on biology has been absolutely immense. Seriously, understanding this algorithm is key to understanding the very backbone of modern bioinformatics. Global alignment is completely fundamental to molecular evolution. We use it all the time to compare genes between species, to help build out phylogenetic trees, and its core principles are the engine behind foundational tools that pretty much every bioinformatician uses, including giants like BLAST and Clustal Omega. And really, that's the beauty of the Needleman-Wunsch algorithm. It takes a computationally massive problem and breaks it down into a simple, elegant process. One matrix, one traceback, one optimal answer. But what if you only need to find the best matching region inside of a sequence? For that, we need local alignment. So join us next time on BioinfoBytes, because we're going to break down its counterpart, the Smith-Waterman algorithm. Make sure you subscribe for more.